Welcome back, amazing physics students. So now we are going to be introduced to a new energy bucket. So we have the kinetic energy, and kinetic energy, as you recall, is 1/2 mv squared. So it relates directly to the motion. The faster the box is moving, the more kinetic energy we have. Potential energy relates to height. So the higher we are off our what we call our zero ground is our potential energy. And so potential energy, and remember that we could use U. So potential energy due to gravity, or UG, equals mgy. Mass times gravity times the height. So since the mass of the box won't change, most of our objects in mass won't change. The gravity stays the same because we're always on Earth, which is helpful. So the thing that does change is our y position. So the higher we are off from our zero, the more potential energy we have. The last bucket that we will see right here is our potential energy due to springs, and you could use that as US. UG you could use for potential energy for gravity. US you could use for potential energy for springs. So remember, energy is just the ability to do damage. So you think of this as if this is a very strong spring and we're pushing it back, pushing the box back, it has the potential to shoot the box out and do some damage. Okay, so Hooke's law. The physicist, Hooke, I forgot his first name, not discovered, but through observation formulated this law. F equals K change in X. F is the force of the spring. K is the spring constant. Change in S, or change in X as you may see it, is the displacement of the spring. It's not exactly how far the box has moved totally. It's just how much you stretch, you compress, or you stretch the spring. The force constant K just tells us how stiff the spring is. A large K means that a spring is very hard to pull apart, to stretch, or to compress. And a very small K would be something that's like very flimsy, easy to stretch or compress. The units for K is newtons per meter. Okay, so let's think of this. We have, and I wish I had the spring here with me, but I don't. Okay, so we have an imaginary spring just hanging. So the unstretched length right here is this, as shown. Okay, so we put some mass on it, and it's going to stretch by distance d. Equilibrium distance, change in S. So, should be a change. I thought I caught all those symbols, but there we go. That's delta S. So, you can find delta S. So we have the unstretched length of the spring as it's hanging. When we hang a box from it, the string is going to stretch down, and this is our new equilibrium. Equilibrium means, of course, the net force is zero. The forces are in equilibrium. There's no sideways forces, but the weight is equal to the force by the spring in this case. Okay? So the stretch, how much the spring stretches, our delta S. Right. Okay. Now, to be completely correct and appropriate, Hooke's law has this negative in here, which means that if we stretch the spring out, the force of the spring is going to go in the opposite direction. It's going to want to pull the box or object back in. And if we compress the spring in, the spring is going to want to push the object out. So that's why the negative is there. The negative is to be completely correct within our system, within our equation. But it's best if you ignore it. If you draw a free body diagram, you are already taking into account direction, which, remember, in physics, negative signs tell us direction. So if you draw a free body diagram, you already know what direction the force is, so you just need the magnitude, so you can ignore the negative sign. So, energy stored in a spring. Energy is stored whenever a spring is compressed or stretched, and it's given by this equation. Energy of the spring is 1/2 K, spring constant. Change in S is the compression or the stretch squared. Another way of writing potential energy for the spring again is US. There we go. And we will be using this in our next example. Okay, have a wonderful day, and I will see you in the next video.